Hello and welcome friends. In the first three modules, we got introduced with the basic concepts of land surveying, related instrumentation, and various methodologies to conduct the surveys. So, having known the basics of conventional surveying, now we wish to enter into the basic principles of advanced surveying. In this particular module, we will discuss about basic principles of electromagnetic distance measurement, abbreviated as EMD. So we'll discuss about the methods of the distance measurement, electromagnetic spectrum, various wavelength regions and their applications, related expressions and methods for electromagnetic distance measurement. So as you learn the content, you will be able to state basic principles of electronic distance measurement as well as also explain methods of electromagnetic distance measurement. So by this time, already you are conversant with some approximate methods, direct methods, indirect methods. So the direct methods could be by making use of tape, by making use of gel. While discussing that linear measuring part, we came to know that there will be considerable mistakes while working on undulating ground, as well for temperature, for pull, for sag, for slope, and such inevitable circumstances, we have to apply corrections for obtaining the correct measurement. Hence, these techniques, taping and chaining, are not suitable in undulating regions. The accuracy that can be obtained is to the tune of 1 in 500 to 1 in 2000. We also discussed about certain optical distance measurement methods which are coming under these indirect distance measurement methods. So we discussed about the various classes of tachometry and we emphasized more on peak steady tachometry. The technique as such is very useful over the rough terrains, undulating regions, but it is useful for limited regions where the length is expected to be measured, say 100 to 150 meters. Because of inevitable component that is getting involved as error in the horizontal distance measurement. As compared to tachometry, substance bar is quite precise methodology to determine the distances, and the accuracy can be obtained to quite a high range. Having known these particular direct measurements and indirect measurements, now we are entering into the class of electromagnetic distance measurement. The basis is employing electromagnetic waves for the distance measurement. In quite an early period, the equipments when employed were jodimeter and tellurimeter. Then the equipment was expected to measure distances to the tune of 15 kilometer to 100 kilometer with the accuracy of 1 in 100,000 with very small measuring fraction. In coming presentations, we will discuss about the constructional aspects of the jodimeter, tellurimeter and some basic methodologies. However, though the literature related with this idiom is simply focusing on the jodimeter as well as tellurimeter, let's agree now that idiom is not just restricted to use of jodimeter or tellurimeter, because both the equipment in the present time are mostly obsolete, and already we have reached to range of the instrumentation which are following almost similar principle of electromagnetic distance measurement. In order to have the horizontal distance, vertical distance as well as even the elevations. Hence, let's not simply focusing on the jodimeter and tellurimeter, but we will consider the electromagnetic distance measurement as an advanced technique for distance measurements. Let's try to understand what is the principle of electromagnetic distance measurement. So basically, we are making use of electromagnetic distance measurement device. This is schematically presented here, which comprises of an emitter which is emitting certain electromagnetic wave. There is a presence of some reflector which is placed at the other end up to which the distance is to be measured. It is in the form of single prism or assembly of the prisms, and in the present period the reflector may be simply a base up to which the wave is expected to reach and travel back. So that could be sort of non-reflector device. As the wave impinges, it comes back and reaches the point of emission, and hence it has to have receiver in addition to emitter. You accept for a time being that there is certain wave which is termed as carrier wave, and we are embedding some information in that wave in order to meet with our basic requirement of sending the information and receiving it back. The wave is termed as modulated electromagnetic wave. As time permits, we'll try to have more discussion with this modulation. So this emitter and receiver are built-in components of this equipment, which is equipped with the obviously telescope. This emitter is expected to work in a certain range which is compatible for that distance measurement. Thus, this electromagnetic distance measurement is totally related with the emission, propagation, reception and reflection, and hence subsequent reception of selected electromagnetic wave emitted from the point of measurement. One more thing we will assume here. What are the factors that you considered about selection of the station, setting the equipment, centering the equipment, focusing the eyepiece, focusing the object glass, hence carrying out the temporary adjustments, and similar concepts are valid for electromagnetic distance measuring equipment also. The kind of the permanent adjustment that we discussed about for the conventional equipment may not be in the hands of common surveyor. However, the kind of the methodologies that we discussed about two-peg test, checking the expected relationship of the horizontal line of sight with the vertical axis of the equipment are valid. So principally, the probable precaution that surveyor has to take in order to obtain the precise measurements are equally true with electromagnetic distance measurement concept. Again, as we move ahead, this concept will be more clearer to you. So this electromagnetic spectrum can be considered in form of radio waves, microwaves, infrared waves, visible waves, ultraviolet waves, X-rays, gamma rays. The kind of the electromagnetic spectrum and the kind of electromagnetic wave that we get, it comprises of electric field and the magnetic field, which are simultaneously propagating perpendicular to each other at higher frequencies. These electrical fields and magnetic fields are not separable, and hence these waves are termed as electromagnetic waves. These waves are characterized by certain wavelength and associated frequency. So, for radio waves, the frequency could be very small, whereas wavelength is quite high. As we move to the right, say for X-rays, gamma rays, frequency is quite high and wavelength is small. In order to meet with the surveying requirements to measure the distances to requisite accuracy, it is not possible to deal with radio waves and waves beyond these visible rays. Hence, the available idiom are resorted to use microwaves, infrared and visible waves. We'll have more discussion with the instrumentation involved for each of these categories. Let's try to understand certain properties of electromagnetic waves. This wave is extremely complex in nature, but it can be presented as periodic sinusoidal wave. Wave completes a cycle while moving through identical points. So, as we consider the point of emission and having the cycle completed up to this particular point, we can express the related distance traversed in form of its wavelength. The number of times this wavelength completes a cycle in 1 second is termed as frequency of that wave and expressed in terms of hertz. A period is the time taken to move through one cycle. The velocity is the distance traveled in 1 second, and it is also related with the medium through which it travels. The frequency of the wave, its wavelength and period vary according to the wave producing source. These terms are interrelated with this expression F is equal to C by lambda is equal to 1 by T, where this C is the velocity of wave in vacuum and it is nothing but the speed of the light. So this velocity of the electromagnetic wave is expressed in terms of V given by F times lambda. So this F is the frequency in hertz, which is in turn cycle per second, and the lambda is the wavelength. In vacuum, the velocity of the electromagnetic wave is same and it equals the speed of the light. In the media, it can be expressed as V is equal to C by N, where this N is refractive index of that media, the value of which is more than or equal to 1. This change in velocity according to the medium through which it travels is determined by noting the change in the refractive index of that medium. The velocity of the light can be considered to be 299,792,458 meter per second, and approximately it can be taken as 3 into 10 raised to 8 meter per second. This F lambda is C by N, and hence the lambda can be expressed as C by f times n. Hence, the refractive index for homogeneous medium varies inversely with the wavelength. If we consider the white light surrounding us, it comprises of combination of the wavelengths, and hence the refractive index for this visible light is referred to as group index of refraction. For electromagnetic distance measurement purposes, the medium through which the electromagnetic energy is propagated is Earth's atmosphere along the line being measured, which may vary from place to place. Hence, it is necessary to determine the refractive index of the atmosphere at the time of the measurement at the location where that distance measurement is being done. So as we discussed, there is a necessity to measure this n for specific lambda. This n varies with the air density and is determined based on the measurements of relative humidity, air temperature, atmospheric pressure at the time of distance measurement for a given location. In order to do so, we have this expression, which includes Ng, capital T, this P and E. This Ng is the group index of the refraction in a standard atmosphere, that is 0 degrees centigrade, where this pressure is 76 millimeter of the mercury. This Ng in turn can be determined by making use of this equation, which is totally based on the wavelength employed for the distance measurement. In order to compute the distance based on the propagation of the emitted wave, we must know the fraction of the wavelength and phase angle. So as discussed previously, this is sinusoidal nature of the wave being propagated. The electrical fields and magnetic fields are perpendicular to each other. As we consider the rotation and simultaneous propagation of both these fields in the direction of the reflector, we can assume this radial vector. So this radial vector completes one revolution as wave travels through a cycle, which is nothing but wavelength. This cycle or the wavelength, having completed one complete revolution, has the phase angle theta as 360 degrees. So, at the point of emission, the phase angle is 0 degrees. At 90 degrees, there is a location of B. For C, the phase is of 180 degrees. For D, it is 270 degrees. And having one revolution completed at E, that phase angle is of 360 degrees. Hence, for these distinguished locations of A, B, C, D and E, the respective fractions can be termed in terms of 0. For B, it is 1/4. For C, it is 1/2. For D, it is 3/4. And for E, it is 1. So these respective fractions may not be simply related with A, B, C, D, E, but it could be related somewhere at intermediate point P. So for such intermediate location, the fraction can be considered in terms of the respective phase divided by 360 degrees multiplied by the wavelength. This consideration is very important in order to determine the fraction of the wavelength during the distance measurement. So let's try to understand now, based on the concepts that we discussed, what is the expression for electronic distance measurement or electromagnetic distance measurement. Having known this fact, wave moves through a constant speed of velocity v over the straight distance, say capital L, in time interval delta t. Hence, that distance would be expressed as L given as v times delta t. As we discussed previously, this v can be put up as c by n. Hence, the distance to be measured L can be expressed as c by n times delta t. For a given wave, for the given location, we know the velocity of electromagnetic wave as well as we have the value of refractive index. Hence, if we could measure the fraction of the time taken in order to move from, say, station A to station B, we'll be able to determine the distance very easily. However, as we discussed previously, the value of the c is to the tune of 3 into 10 raised to 8 meter per second. And hence, the measurement of the interval delta t will need highly advanced instrumentation and it needs to be measured with extreme accuracy. This is very difficult proposition and hence this electromagnetic distance measurement is based on this expression L is equal to m plus p into lambda. So as we consider emitter and reflector, The distance is measured through propagation of the electromagnetic wave till the reflector and its coming back and subsequent reception. Hence, though the distance AB is L, in reality it is measured as 2L. Till this station B, number of whole wavelengths could have been covered. However, certain portion could be left in the form of fraction of that wavelength as shown small p here. Hence, this L is number of times whole wavelengths plus the fraction of the wavelength till the station up to which that distance is to be measured. Hence, for given equation, in order to determine this L, we have to have lambda, number of whole wavelengths and fraction of the wavelength that is covered till the point up to which we wish to measure the distance. As we extend this particular discussion, we have to understand two more terms. So, based on our earlier discussion, wave is transmitted from station A, reflects from B and received at A again. Hence, the distance covered by that wave is 2L, which is given again as n lambda plus delta lambda. This determination of the fraction of the wavelength is known as phase comparison, and it is done by making use of phase detectors. As we discussed previously, lambda corresponds to phase angle of 360 degrees. In order to have that fraction determined, we must have phase of the wave as it is transmitted at A, which could be 0 degrees, and the phase of the wave as it is received at the point of the emission. So, having known this theta 1 and theta 2, we can determine this delta lambda as theta 2 minus theta 1 divided by 360 degrees times lambda. So, by comparing the phase of the wave returned from the reflector with the reference wave, an idiom can measure how much the two waves are out of phase with respect to one another. As we discussed here, we are simply focusing on the delta lambda, but we are not determining this n lambda. So at the instant of the measurement, after propagation we can determine the value of delta lambda, but still that n lambda is not known to us. This determination of n lambda is known as resolving the ambiguity of phase comparison. So there are two methods. Method 1 is we increase the wavelength manually in the multiple of 10 to determine the distance approximately. In second method, we measure the same distance using 3 different wavelengths so as to get the set of simultaneous equations, and by solving the same, we will be able to determine the value of n lambda, which is nothing but resolving the ambiguity. Every idiom has got the provision to solve these particular equations through the built-in microprocessors and to display the results on LCD instantaneously. So, having known determination of delta lambda as well as n lambda, we can move on to actual distance measurement by idiom. So here we have four methods. The first one we considered in terms of time taken multiplied by velocity, and as we discussed, this method is not appropriate as we deal with very high velocity of electromagnetic wave. In addition to this technique, there are three methods. One is frequency shift measurement, phase shift measurement, phase shift, and the number of full cycles measurement. So let's try to understand each one of them. In many idiom systems, the modulation frequency can be changed by small increments, which allows the distance to be measured by recording consecutive frequencies that return to zero phase angles. The frequency is set such that L by lambda 1 is equal to n. If this frequency is slowly changed, then the phase difference will still be non-zero, but it will return to zero again at slightly different frequency, so that L by lambda 2 is equal to n plus 1. If we are very much certain that lambda 1 and lambda 2 represent exactly one cycle difference over the distance capital L, then the two equations can be solved for L. So we have this L by lambda 1 is equal to 1 initially. After changing that particular frequency, slowly we will be getting the expression L by lambda 2 is equal to n plus 1. Hence, this L by lambda 2 minus L by lambda 1 has to be 1. So as we solve for L, based on the wavelengths, we will be able to determine the distance. Here, the accuracy of L solely depends on the difference in the two wavelengths being employed. The other technique is measurement by phase shift. Here, the equipment sends electromagnetic waves of increasing wavelengths. The shortest wave provides the smallest digit to the right when its fraction is in hand. As the fraction of the longer waves are measured, each longer wave provides the digit to the left and also provides the check on the computation that we did with the result that we receive with shortest wave. We'll try to understand through certain example. So for a given instrument setup, as you see here, there are a range of frequencies being reduced 1/10. Corresponding to that, the shift of these phase angles are also determined. The speed of the electromagnetic wave is 29792.452 meter per second and the refractive index is 1.003. Hence, for a given situation, the actual velocity of that electromagnetic wave will be 29792.458 divided by 1.0003. So with this computed speed taken as c, for the given frequency, the wavelengths can be determined as 0.2, 2, 20, 200 and 2000. The effective wavelength, which is half of that wavelength, can be taken as half of the values computed here. As we discussed initially, that phase shift fraction by 360 degrees can be computed, and hence the distance can be measured as 0.083, 0.78, 4.7, 14 and 31 for set of the frequencies and phase angles that are measured at that location. So, for this given phase angle of 298.7975, respective effective wavelength of 0.1 meter, hence 298.7975 divided by 360 degrees into 0.1 will give us 0.083. Similarly, this 280.7976 divided by 360 degrees will give us that 0.78, and so on as we reach the distance of 31 meters. If this distance is taken as A, B, C, point D, F, it can be determined as 314.783. So the way that red digits are presented here. So for this example, the number of full cycles for 1000 meter wave having the distance less than 1000 meter will obviously be 0. As we consider the wavelength of 100 meters having the distance 314, the number of full cycles have to be 3. For 10 meter wavelength it will be 31, and for 1 meter wavelength it will be 314. The distance measurement is also possible by phase shift and number of full cycles. In this method, the longest wave is longer than the maximum range of the instrument. So for example, if the instrument can measure up to 10 kilometers, the longest wave used should have an effective length more than 10 kilometers, say for example 20 kilometers. The phase shift of the longest wave determines the length to about 1%, but it can also resolve the ambiguity of the next shorter wave. Say for example, if the phase shift of 20 kilometer wave is 320 degrees 24 minutes, it will result in terms of the fraction 0.89 lambda. So 320 degrees 24 minutes by 360 degrees is nothing but the 0.89 lambda. The length will be 0.89 times the wavelength, which is 17,800 meters. Say, if we are making use of wavelength 5 kilometers subsequently, so for the distance of 17,800 meters, the number of full cycles, which is ambiguity, will be 17,800 divided by 5, which is 3 waves. For the given case, if the fraction of the 5 kilometer wave is 0.55, then n lambda is 3, whereas delta lambda is 0.55. Hence, the distance will be 3.55 times 5,000, which is 17,750 meters. As such, each wavelength solves the ambiguity of the following shorter wavelength, the way we discussed about employing 20 kilometer and 5 kilometer wavelength, and the phase shift solves the fraction of that shorter wave, and so on. So the subsequent wavelength that is employed with the shorter wavelength will improve the accuracy of the result of distance measurement. So here we are employing 3 different wavelengths: lambda 1, lambda 2, lambda 3. By making use of number of full waves and fraction of 8, we will be able to determine that L, this P1, P2, P3, which is the fractions corresponding to theta 1, theta 2, theta 3, can be determined, which will assist us to determine distance L. For example, say if lambda 1 is 10 meters and the constant is of 10, respective fractions determined for lambda 1, lambda 2, lambda 3 are P1, P2, P3 as shown here. So that lambda 2 will be k times lambda 1, hence 100 meters, lambda 3 will be 1000 meter. So the way we considered earlier, manual increase in 10 times turn, the same thing is done here. So corresponding to lambda 3, having the wavelength greater than the distance to be measured, this number of full wavelengths will be 0. That fraction is given as 0.1250. Hence, the distance will be approximately 125 meters. Subsequently, we have employed shorter wavelength lambda 2, which is 100 meter. So for that, we can determine the ambiguity 125 by lambda 2. Here lambda 2 is 100. Hence, the number of full wavelengths determined will be 1. So, subsequently, this L can be determined as 1 plus P2, which is 0.2620 multiplied by the wavelength, and hence the result is refined as 126.2. As we multiply this, as we divide this 126.2 by wavelength 10 meters, this number of full wavelengths lead will be 12. Hence, 12 plus 0.2562 into 10, which is 122.56, 2 gives the refined measurement. Same thing is again discussed by using different data. So here we have various wavelengths employed, 20 kilometer through 0.5 meter. The fractions that are determined are available here. So the resolved wavelengths for 20 kilometer wavelength, value of m is 0 plus p as we considered in our earlier example, which comes to be 0.59. So 0.59 times 20 kilometers. So distance here determined is 11800. Subsequently, we have employed the wavelength of 1 kilometer. So here, that number of full wavelengths, which is ambiguity, 11800 divided by 1000 will be 11.8. Hence, the resolved wavelength will be number of full wavelengths, which are 11 plus that fraction in terms of 0.79. So as we multiply this 11.79 with 1000, we'll be getting the distance. So same way as we proceed further, we'll be able to get the refined measurements as 11785.35 through the computations that are shown here. Hence, at the end, the result can be taken as 11785.35 meters. So the ambiguity shown 0 for 20 kilometers, 11 for 1 kilometer, 58 for 200 meters, 1178 for 10 meters, and 23570 for 0.5 meter. So, thanks for your attention. I hope the concepts that we tried to discuss with the electromagnetic distance measurement are clear to you. As we move ahead, based on the discussion that we made, we'll discuss about types of various equipment for electromagnetic distance measurement. So bye till then, I wish you very happy learning. Thank you.